So this is part 2 of our examples for our financial mathematics topic, and we're basically just looking at using the tools and methods that we've talked about throughout this topic to evaluate single projects and to compare 2 or more projects. So we took a look at 2 different examples in part 1, and so what we're going to do now is take a look at a third example, a bit more complicated. So if we just take a look here, we've got 2 different cash flow series. So we've got project A involves a $5,000 initial outlay. Nothing occurs in year 1. And then we've got a deferred annuity of $500 for the next 2 years and a deferred annuity of $1,000 for the following 4 years. For project B, we've got a $2,000 outlay and then a $300 annuity in the next 4 periods and a $1,000 final period cash flow inflow. And what we're told is that our MAR is 12% per annum compounded monthly. So the things to note for this is that if we're going to compare these projects, they're of different useful lives. We've got a 7-year useful life here and a 5-quarter useful life for this project. So we can't simply calculate the present worth of the projects. So what we have to do is calculate the equivalent annual annuity in order to compare them. So if we calculate the equivalent annual annuity, we can therefore work out which one has a greater annual worth. Now, embedded assumption in this is that the projects can be repeated indefinitely. So whenever you're doing a question on this, just remember to state your assumptions. So the main assumption is that the projects can be repeated indefinitely with identical cash flows. The second piece of information that we need to deal with is that we have a 12% per annum compounded monthly. However, the cash flows in project A are occurring yearly, and the cash flows in project B are occurring at the end of each quarter. So we're going to need to adjust this accordingly. So looking then here, so I've put down to compare projects of different useful lives, we need to determine the equivalent annuity, and in this case the equivalent annual annuity, and we need to assume repeatability. So the step 1 is to determine the appropriate discount rates to use. So we're given 12% per annum compounded monthly, but for project A we're going to need yearly cash flows. So using the effective interest rate formula, we've got monthly, so we've got 12 here, and we want annually, so we've got a 1 here, and we get a 12.68%. In project B we have quarterly cash flows, so again we have 12 because we're given a monthly, but we want quarterly, so we have a 0.25. So we therefore have an effective interest rate of 4.06% per quarter. So sometimes it's easier to determine your equivalent annuity by first determining your present worth. So in this case that's what we're going to do. So for the first problem we have a discount rate of 12.68%. We have an initial outlay of $5,000, and then remember we have a deferred annuity in periods 2 and 3 of $500. So it's occurring for 2 periods and it's a deferred annuity. So calculating the present worth of this will take us to the end of year 1, and so we need to go back 1 more year to calculate to year 0. So just looking at it here, deferred annuity, so calculating the present worth of this will take us to year 1, so we need to go back 1 more year. And similarly for the $1,000, it's for 4 years, but it's deferred and occurs in periods 4, 5, 6 and 7. So calculating the present worth will take us to the end of year 3, and so we need to go back 3 more years. So the present worth of A is therefore negative $2,163.74. Doing the same for project B, we've got an initial outlay of $2,000, then an annuity of $300 for 4 years, and this is our quarterly discount for 4 quarters, and this is our quarterly discount rate. And then we have a $1,000 single cash inflow at the end of the 5th quarter. So bringing that back 5 quarters, we get a present worth of negative $93. Now don't be fooled by that. Remember, this is only over 5 quarters, whereas the other one's over 7 years. So even though it seems much greater, it's going to come out relatively closer than this. So now we need to determine our equivalent annual annuities. So we've got a present worth of this, and we're simply just going to divide by the factor that you normally use to calculate your present worth. So we're basically finding this factor here. So over the 7 years, we get negative $484.22. Now for project B, remember that we're not going to be using the quarterly discount rate. We want to use the annual discount rate because we want to figure out our equivalent annual annuity. So that's something that gets people quite confused. We've already figured out the present worth. It doesn't matter how that project's compounded. We now want annual cash flows, and therefore we need to have an annual compound rate. Now it's 5 quarters, which is the same as 1.25 years. So we're just going to figure out the equivalent annual annuity over that period, and it's $85.07. So neither of the projects are desirable because they're both got a negative annual worth or present worth. But if one had to be chosen, we would choose B because it has a much lower cost. So don't forget that although if this were positive, we'd choose A, if it's negative, we'd choose B because we want something that generates the lowest cost.